Hi, this is Mrs. Boland with the University of West Florida. Welcome to College Algebra, section 6.7. Today we're going to be learning about exponential and logarithmic models. So real-life models with the exponential function and the logarithmic function. So let's get started. So the first thing we're going to talk about is just a real-life model here. It says the population of India was about 1.25 billion in year 2013 with an annual growth rate, so this is an annual growth rate, this is key, of about 1.2%. The function, and then we have a mathematical equation, okay? Models, so this is our model, our mathematical model, where this growth rate t is the number of years since 2013. To the nearest 10,000, what would the population of India be in year 2031? So the first thing we want to do is solve for t. So step one, we need to solve for t. And this one here is kind of simple. T, which is time. Let me write that down. Which is time, okay? So how many years from the current starting time will it be? That's really the question. So we need to know, we're going to use this model to predict the population in 2031. So we're going to say 2031, and we're going to minus our initial year. And our initial year was 2013. So 2013, that difference is 18 years. So we're going to say for 18 years worth of growth, what are we projecting our population to be? So we're going to plug it in like this. We're going to say, what is P sub t when t is equal to 18? We have to look at the number of years that it's growing. And that's going to be equal to this model right here, 1.25 times 1.1012 raised to t. And what does t equal? It equals 18. Grab your calculators. I should have said, make sure you have your calculators for today's lesson. If you don't have it, this is a great place to pause the video, go find it, and then push play when you come back. So when you punch this in your calculator, you are going to find that it is equal to 7.08764. And it says to round to the nearest thousandths. So we're going to say that P of 18 is equal to 7.088. That's the nearest thousandths, and rounding up accordingly. Now, to put this in the TI 30XA, let me show you I'll write down the shortcut for that real quick in case you're not sure how to put it in. So it's the TI 30XA. Order of operation is very important. So you're going to put in 1.1012. We're going to start with this part right here, and we're going to raise it to the 18. So then we're going to hit, the next button we're going to hit is y to the x, and then after that you're going to put 18. You're going to hit the equal button, and then you're going to hit the multiplication, which is x. Let me change that out. I want to put that as a dot, so it's clear multiplication, and then it's 1.25, and then equal. Okay, and when you do that, your answer will be 7.088. So going on to example number 2. It says a can of soda is placed inside of a cooler. As the soda cools, its temperature, which is denoted by T of x, in degrees of Celsius, is given by the following exponential function, where x is the number of minutes since the can was placed in the cooler. So again, we're giving a mathematical model that tells us how the temperature changes and fluctuates once it's placed inside the cooler. It says find the initial temperature of the soda and its temperature after 15 minutes. Round your answer to the nearest degree as necessary. So again, our initial temperature, initial time is t equals 0. So we're going to put that in because our initial time, it says find the initial temperature of the soda. So our initial temperature is going to happen at time 0, right when we start. So we're going to let time be 0. So our temperature when time is equal to 0, so we could have just written this as T of 0, is equal to this formula right up here, negative 22 plus 46 e raised to the negative 0.41 x. What is x equal? X in this case is going to be equal to 0, and it should be, I guess, t on that. So this will be 0. Okay, we're going to let the variable be t right there for time. Alrighty, so next we're going to plug this in our calculator, and when you do, you're going to find out that this, you could just rewrite this and you should be able to notice that this is negative 22 plus 46 times e. 0 times anything is 0, which makes this 1, correct? So this is negative 22 plus 46 times 1, which is going to be equal to 24 degrees Celsius. Okay? Now, that was when time is equal to 0. Let's look at it when time is equal to 15. So this one here will be when time is 15 minutes. Okay, so I can let t equal 15. Little t, that's my variable. They use x, I'm using t because it makes a little bit more sense. So my function, evaluate it when the variable is equal to 15. Looks like this. It's negative 22 plus 46 e to the negative 0.41 times 15. And that is going to be equal to negative 21.9 degrees Celsius. Round it to the nearest degree is negative 22 degrees Celsius. So that is our answer. To put this in our TI-30XA, so our TI-30XA, here's the order of operation. You're going to put in 0.41. You don't have to put the leading 0 in. And then you're going to go plus or minus. It's the button that is right below the 3. Okay, that's where you change it to a negative. And then you're going to multiply it by 15. And that is equal to, and then you're going to hit equal, and then you're going to take the second. You're going to hit e to the x. You're going to multiply by 46. You're going to subtract 22, and then you're going to hit an equal sign. And if you follow this order of operation with the TI-30XA, it will equal negative 21.9, which rounds to negative 22 degrees. So after 15 minutes, we will be at negative 22 degrees. Next, we're going to learn about exponential growth and exponential decay. A prime example right now, if you've been watching the numbers on the coronavirus, that's a prime example of exponential growth that we've been seeing with the increase. There's a world meter, if you go and you can look at that. It has graphs underneath the statistics where they're keeping actual counts of numbers. And if you look at the model of the graph for the United States, you'll see it's a perfect exponential growth function. So that's exactly what we're talking about when we're talking about real life applications and situations. So let's review a growth versus decay. So when y is equal to a times, you got to look at the center here, 1 plus r, that's when we have a exponential growth, okay? So when we have 1 plus r right here, it is a growth. When we have 1 minus r, that's when we have a decay, both at the rate of r. So example 3 says, determine if each function is a growth or a decay exponential and give the rate of growth or the decay. So first determine if it's a growth or a decay, and then determine the rate, okay? So we look at this very first function right here, and what we need to look at is what's within the parentheses right here, because that is where we determine if it is a growth or a decay. If this value is greater than 1, then we are going to have a growth. If it's less than 1, then we're having a decay. And we'll take that number, whatever it is, in this case it's 1.275, and we're going to set it equal to, because it's greater than 1, we're going to set it equal to 1 plus R, because we have a growth, okay? Again, because 1.275 is greater than 1, we have growth. Okay, now all we have to do is solve for R. So I can subtract 1 from each side, and I get 0.275 is equal to R. If I wanted to take and put it as a percentage, then I would say that our rate is equal to 27.5. How about 27.5? We'll get that right, percent. Okay, let's look at the second problem right here. Again, looking at this number that's in the parentheses, you base whether it's a growth or decay off of the value of that number. Since that value is less than 1, we know that we're dealing with a decay. So since 0.62 is less than 1, we have decay. Okay, so we evaluate the number right there. To solve for that number, we're going to let 0.62 equal to the function for decay, which would be 1 minus R. Again, we're going to solve for R, so I can subtract 1 from each side, and I'm going to get negative 0.38 is equal to negative R. Multiply both sides by negative 1, and I'm going to get R is equal to 0.38. But if I want to put it in percent, it's going to be 38%. Alrighty, so hopefully you know how to recognize if a function is a growth or a decay. Decay meaning decreasing function. An exponential growth or decay function can also be modeled by the following function, which is more common in real-world applications. So for the initial amount, we always have an initial amount where Y naught, okay, Y naught is your initial amount. It has to be greater than 0. We can't start out in the negative, okay? We have to have something to begin with. Our equation looks like this. Y is equal to Y naught e to the kt. And this defines a growth function if and only if k is greater than 0. So you have to look at the k for this particular model to determine if it is growth or decay. It defines a decay function if k is less than 0. Okay, so you have a negative there. The growth rate or decay rate is k. And the equation is also used for continuously compounding situations such as money. We're going to continuously compound on interest on an investment. That's a good thing. Or on your mortgage, not such a good thing. An initial amount of $1,100 is invested into an account at the interest rate of 2% per year. So this is our initial investment. That would be Y naught. Our rate is 2% and it's compounded continuously. Find the amount in the account after 4 years. That's our time. Round your answer to the nearest cent. So we're going to keep it in dollars and cents. So the question is find the amount in the account after 4 years. So we're going to say that our formula is Y is equal to Y naught e to the kt. Our initial investment amount is denoted by Y naught, and that is equal to the 1,100. So that's 1,100. Okay, and then our K is the percent that we're investing. So R is equal to 2%, but we need to change it to a mathematical notation. So it's going to be 0.02. Then it says our time T is 4 years. So 4 years. So we're just going to plug everything in and find out what y is equal to. So we have y is equal to 1100 e to the 0.02 times 4. Plug this in your calculator and you're going to find that that is equal to $1,191.62. Okay, grab out your calculators, duplicate this because you need to know how to do this. For the TI-30XA, here's how we punch it in. You're going to put in 0.02 and you're going to multiply it by 4. Then you're going to hit equals. Then you're going to hit the second button and the e to the x after that. Again, you're going to multiply it by 1100 and hit equal. And when you do that, you should get $1,191.62. I'd like you to take and pause the video, solve number 5 on your own, and then push play to see if you got it right. This one here is just simply asking you to solve for why not. Set the problem up, write down everything that you know, put it into the formula that we found right back here. Let me see if I can scroll back down to this formula right here. Okay, you're going to use this formula right here, and then push play after you've solved it to see if you got it right. I'll see you back in just a moment. Okay, so we're going to read the problem and solve this one together at this point. An initial amount of money is placed in an account at an interest rate of 5% per year, and it's compounded continuously. After 2 years, there is $1,934.05 in the account. Find the initial amount, that's why not, placed in the account. Round your answer to the nearest cent. So our formula looks like this. It's y is equal to y naught e to the kt. So what we know is that after so many years, we had $1,934.05. That's y. So y is equal to $1,934.05. We know that k is our rate, which is 5% per year. So let's go ahead and write that as a math number, not just 5%. And then how many years did we invest? 2. So t is equal to 2 years. Let's plug everything into this initial formula right here and see what we know. We know that $1,934.05 is equal to y naught e to the 0.05 times t, which is 2. Now what we need to do is solve for y naught. So the first thing we're going to do then is divide both sides through by e to the 0.05 times 2. This is nothing but a number. This number is attached to our variable by multiplication. To undo multiplication, we're going to use division. Just leave this in this form. Do not change it to a decimal form, especially for web work, because you will probably get a wrong answer. It needs to run out in decimal places. So we're going to divide both sides through by e to the 0.05 times 2 on both sides. And you can change the 0.05 times 2. That you can do, and if you want to, you just change it to 0.1. That's not a problem. So over here, this crosses off. So now all I have right here is y naught. So I say, therefore, y naught is equal to 1,934.05 divided by e to the 0.1, because 0.05 times 2 is just 0.1. Grab your calculator, throw it in, and you're going to find out that the calculation is 1,750 $50. So that is how much we initially invested at the beginning with our investment, okay? And then after 2 years, that $1,750 grew to $1,934.05. So that was a positive return. For our TI-30XA, here's how you would input this. You would go 1,934.05 divided by, open parentheses, open another parentheses. It's going to be 0.05 multiplied by 2. Close one set of parentheses, hit your second button, then hit E to the X, close your last set of parentheses, and hit equal. And that's what you're going to need to do, and it should equal $1,750. If you got this correct, please email your UWF professor the code word hot dog, okay, because you got it right. If you did not get this problem correct on your own, that's okay. We appreciate you trying, but we would like the code word for attendance to be the word bike, B-I-K-E. So if you got it right, send us the code word hot dog, and if you got it wrong, send us the code word bike, and then we know that you watched the video, and we will mark you for attending class for this lecture today. According to the U.S. Census Bureau, the world population reached 6 billion on July 18th, 1999, and was growing exponentially. In other words, continuing to grow at a rapid rate. By the end of year 2000, the population had grown to 6.079 billion. Projected world population in billions, T number of years after 2000, so year 2000 is our initial count year, is given by the function right here. Based on this model, what will the world population be in 2015? Again, I want you to pause the video and try to solve this one on your own, then push play once you've solved it. Okay, welcome back. The first thing we need to do is figure out what T will be. So how many years have we had the growth increasing? So they're asking about 2015. Our initial year is 2000. So we do the subtraction, and so we get 15 years. All we have to do then is say, what is f of t when it is equal to 15? We're going to use this function right here. And that is going to be equal to 6.079 e to the 0.0126 times 15. Put that in your calculator, and you're going to find out that that is equal to 7.343 billion. Okay, and did it tell us to round? Let's see here. No, it did not give us a rounding. So if you got this right here as your answer, again, for attendance purposes, please make sure you text or email your UWF instructor the code word fish. And if you got it wrong, please email or text your UWF professor the code word shell. Okay, part B. It says, in what year will the world population reach 8 billion? So what we're asking is, when will this side of the equation be equal to 8 billion? So let's write that down. It's going to be 8 is equal to this function right here, 6.079 e to the 0.0126 t. And again, it says in what year. So we're solving for t right here. In order to solve for t, the first thing we're going to do is we're going to move our 6.079 over here to the left. What we do to one side, we must do to the other side. Do not take this fraction. I know it's a fraction with a decimal in it. Don't modify that. Leave it in that form, because otherwise on your web work homework you will not get the right answer because of the rounding errors that it will induce. So now we have 8 divided by 6.079 is equal to e to 0.0126 6t. I need to solve for t. In order to do that, I need to take the natural log of both sides. I'm choosing the natural log because I have an exponential function right here. So what I do to one side again, I must do to the other. So I have the natural log of 8 divided by 6.079 is going to be equal to the natural log of e to the 0.0126t. Remember that when I take the natural log of e, the first thing I can then also do is apply the power rule. So let's come over here and just do a little other math real quick. So if I have, I'm just going to do this up here real quick. So if I have the natural log of e to the 0.0126t, I apply the power rule. So that's going to be 0.0126t natural log of e. Well, what is the natural log of e equal to? The natural log of e is also equal to log base e of e, correct? So now I can set this equal to x, and I can solve for x to see what does x have to equal to make this a true statement. Well, if I rewrite this then as an exponential, it would be e to the x is equal to e. So I get e to the x equals e. What value must x equal to make this a true statement? It must equal 1. Therefore, x equals 1. If x equals 1, that means the natural log of e equals 1. If the natural log of e equals 1, this right here will equal 0.0126t. This right here equals 1. 1 times this is just this right over here. Okay? So with that said, I now know that I can say that this statement right here is equal to 0.0126t. I need to solve for t. In order to solve for t, I'm going to divide both sides right here, 0.0126, and over here by 0.0126. And now I have, therefore, t is equal to the natural log of 8 divided by 6.079 divided by 0.0126. Grab your calculator, put it in your calculator, and you're going to find that therefore t is equal to 21.79. So that's 21.79. That's what t equals. It didn't ask how many years it will take for us to reach 8 billion. It said, what year will we reach 8 billion? So our final answer actually is, it says, what year? Make sure you always answer the question that was asked. So our year would be, we're going to start in year 2000, and we're going to add to it essentially 22, right? So we'll add 22. So year 2000 plus 22 would be the year 2022 is when we will have reached 8 billion, or during the year 2021, okay? Halfway through, or a little bit more than halfway through year 2021. But by year 2022, we will have reached 8 billion. Our last problem for today is right here. And it says, how would we set up a problem if we wanted to know when the population would double from its size in 2000? It's going to be, we need it to double. So initially, in year 2000, we know that we have y is equal to 6.079 e to the 0.0126t. This is our formula. This right here is y naught in year 2000. if I want to know what year it will have doubled, I need to solve for t. But what value do I put over here? Well, what about 2 times 6.079? Because that's our initial amount. Doesn't that make sense? So we'll say 2 times 6.079 is going to be equal to 6.079 e to the 0.0126 t. That is how we would set it up. We would take our formula right here, our function, and we would set it equal to 2 times the initial amount. There's our initial amount. So if we wanted to go ahead and solve for t, the first thing we would do is we would divide both sides through by 6.079. What I do to one side, I'm going to do to the other side. It actually crosses off there and there. So what I end up with is just the 2 over here. So it's 2 is equal to e to the 0.0126 t. We need to solve for t, so we're going to take the natural log of both sides. So we'll have the natural log of 2 is equal to the natural log of e to the 0.0126 t. I'm going to apply the power rule. So I get the natural log of 2 is equal to 0.0126 t natural log of e. Remember that the natural log of e is equal to 1. Okay, so this is really just equal to 0.0126 t. I need to solve for t, so I'm going to divide this by 0.0126. So what we do to one side, we must do to the other, so we're going to divide both sides through by 0.0126, and then over here by 0.0126. That goes away, and all I have left is t, so I get, therefore, t is equal to the natural log of 2 divided by 0.0126. We'll put that on our calculator, and we're going to find that t is equal to 55.01. So essentially, 55 years from now, or from our initial start time, we will have doubled in population. So our actual answer is 2000 plus 55. So that's 2055 is the year that the population would double. Okay, so practice not only doing real life or real applications here in your homework, but make sure you're using the calculator you plan on using for next week's exam so that you're very familiar with your calculator and you know how to use it. Because I can tell you right now, there's nothing much worse for a college algebra instructor than to see somebody who's understanding the concept but who doesn't understand how to use their calculator properly. So work hard, make sure you understand how to do the concepts as well as your calculator. Thank you for listening, and since you made it to the end of the video, please text or email your UWF instructor the code words stormy night. Have a good day.